All right, let's take a look at the final individual gas law that we'll be studying. It's called Gay-Lussac's law. We just abbreviated the GL law. So let's recap. We know that Boyle's law is a simple law that says that P1V1 equals P2V2. And this is the law that says that pressure and volume are inversely related. And, inverse. We also studied Charles' law, which is a simple mathematical relationship. It says V1 T1 equals V2 over T2. And what this says is that volume and temperature are direct, meaning a direct relationship. Today, we're going to look at our final law. Let's go to our little simulator. And what we're going to do today is explore the relationship between pressure and temperature. So let's go there. Here we have in our simulator a bunch of gas particles bouncing around, and we'll keep the volume constant. But notice that we've got our pressure gauge in atmospheres, and we've got our temperature in kelvins. And let's try to predict what's going on here, because the volume is going to be fixed. So what's going to happen? Well, we know that we're going to increase the temperature, and we know that that's going to increase the velocity of our gas molecules. What's that increased velocity going to do to our pressure? Well, we know that as molecules move faster, they impact the sides of the vessel faster. That's what we call pressure. So let's see what happens when we increase the temperature. And not only do we see these molecules moving faster, but look what's happening to our pressure gauge. As our temperature climbs, our pressure increases, and we're going to hold our foot to the gas here and see what happens, because as our temperature increases, notice that our pressure gauge is also heading for the red line until, boom, the lid blows off our vessel. What analog do we have for something like this in real life? Look what I found in the back room. I found a can of black spray paint, and what's most important about this is that it's in an aerosol can. You just take the cap off and hit the button, and we can spray this on anything. That's how we use spray paint. But let's take a look at what it says on the back. Obviously, there's quite a lot written here, but let's focus on a couple of lines in particular. It says, contents under pressure. Avoid prolonged exposure to sunlight or heat from radiators, stoves, hot water, and other heat sources that may cause bursting. Do not puncture, incinerate, burn, or store above 120 degrees Fahrenheit. Interesting that it mentions heat. In fact, it says up here, it says, look, extremely flammable. Keep away from heat, sparks, and open flame. Vapors will accumulate readily and may ignite explosively. Interesting. Let's focus on this pressure part when it says contents under pressure. Let's explore this a little bit. What happens, for example, if we light one of these on fire?
An eye-opening lesson this week for Coon Rapids firefighters.
This is what happens when flames meet aerosol cans. It was quite a scene Tuesday inside the old Firestone building on Coon Rapids Boulevard. The fire department conducted several test burns in the building, which was purchased by the city for redevelopment. It didn't take long before aerosol cans turned into missiles. The test has the fire department recommending residents keep aerosol cans in their garage in a metal cabinet.
Best thing to do is, keep your cans like in a metal container so they can't be exposed to the heat, and try to limit the cans you have. If you have aerosol cans or WD-40 cans that are empty get rid of them.
The Coon Rapids Fire Department responds to about 20 garage fires each year. The lessons learned this week will be passed along to all firefighters in the hopes of keeping them safe.
Obviously, that clip's pretty spooky, but I want to focus on one point in particular. Let's rewind the tape a little bit and pause it at my favorite spot. Okay. Watch this. Do you see it? Pretty interesting. These things release this pressure so violently that they become literal missiles. Pretty spooky. So, good advice to listen to. So, this is our third individual gas law. We're going to call this Gay-Lussac's law. I just call it the GNL's law. And what it says is that, obviously, pressure and temperature are directly proportional. That means that as one increases, the other increases, and vice versa. Mathematically, we're going to represent it with this equation. P1 over T1 equals P2 over T2, where obviously P1 and T1 are initial pressure and temperature, and obviously P2 and T2 are the final, or the new, pressure and temperature. And remember that because we're dividing by temperature, that temperature must be in kelvins. Okay, so let's take a look at one and we'll try this out and see how this works. So let me get an example going here. So here's the type of question you can expect me to ask. A gas exerts a pressure of 1 atmosphere at 25 degrees Celsius. What will the pressure be if the temperature is increased to 300? So remember that I like to establish my variables. I like to know what it is that I know and what I'm looking for. So we know that initial pressure is 1 atmosphere. We know that initial temperature is 25 degrees Celsius, but we gotta get that into kelvins by adding 273, so we'll call that 298 kelvins. We're trying to find the new pressure at a new temperature of 300 degrees Celsius, otherwise known as 573 kelvins. So let's plug them in to our equation. We know that the GNL's law is P1 T1 is equal to P2 over T2. So P1, 1 atmosphere, T1, 298 kelvins. P2 is what we're trying to find, T2, 573. So we'll get P2 by itself by multiplying both sides by 573. So now what we have looks like this. And all that is equal to P2. Now, I'm a big believer in paying attention to the units. So we know that we're dividing kelvins by kelvins. That means they will cancel. And all that's left is atmospheres, which is what we want, a unit of pressure. So 1 times 573 divided by 298. Now, before we get our answer, I like to predict what we think is going to happen. We know that temperature and pressure are directly proportional. That means that as one increases, the other increases, and vice versa. Well, the temperature increased. It went from 25 degrees Celsius to 300. It went from 298 kelvins to 573 kelvins. Do we expect the pressure to decrease or increase? Because we know that they're directly proportional, I expect the pressure to increase too. From 1 atmosphere to 1.92 atmospheres. And that is GNL's law. So I'd like you to take that one for a spin, please, and we'll see you on the next one.